On January 2nd of that year, a typically frigid winter day, a 40-year-old tank was being refilled for the first time after being disassembled in Cleveland, Ohio, and reassembled in Floref. Then, in less than 1 second, the tank cracked vertically, releasing a tidal wave of about 3.8 million gallons of oil.
When the tank split, the force of the weight of oil in the tank pushed the shell of the tank, the skin of the tank, back against this dike wall in this direction.
The oil rushed over the containment dikes in front of the split, hurtling toward other nearby tanks.
When the tank that collapsed, which was behind me, released the oil, the tank that was formerly in this direction was dented by the force of the oil approximately 20 feet up on the wall of that tank. The tank was empty, but it gives you some perspective on how much force there was involved.
While some oil remained inside the dikes, the faster parts of the flow raced over the final barriers at the south end of the facility.
When the oil went off to my right, it went over the last dike in that direction into a parking lot. The parking lot has a drain in it. The oil followed that drain into the Monongahela River.
Experts estimated that between 700,000 and 800,000 gallons of oil entered the river, making this the worst oil spill in the history of this industrialized valley. The north-flowing current of the Monongahela carried the oil past a number of smaller communities, into Pittsburgh and beyond. Towns along the river were forced to shut off their water intake systems. Tens of thousands of people were without regular water service for up to 8 days. Overall, the spill temporarily contaminated drinking water supplies for about 1 million people in Pennsylvania, Ohio, and West Virginia. Contractors hired by Ashland used booms and other equipment to collect as much oil as possible from the river's surface. By the time John Gross and other investigators arrived, the oil in the dike areas had been pumped out to barges.
It was very obvious from just standing on one of the dikes, a full view of the tank, to see that it had split vertically and had begun to unpeel, like you would unpeel an orange.
When the steel split, it left behind arrow-like markings, similar to the chevron stripes on a military uniform.
We found the chevron markings along this area to be pointing down, and the chevron markings along this area to be pointing up. And so just about at eye level was the confluence of those two, and this is where the fracture initiated.
At that spot was a dark area about 3/4 of an inch long. This is where it had all started.
This is a close-up of the defect in the tank wall. You can see it's this dark area here. And that dark color is caused by the carburization, which is a result of the combination of carbon and oxygen, which is present in the cutting operations that were used in either putting the tank together the first time or in reassembling.
Even today, small defects like this aren't uncommon in these huge tanks. It's hard to prevent such imperfections during large cutting and welding operations. But ordinarily, weak spots in modern tanks lead only to small leaks, which can then be easily repaired and cleaned up. Because of the speed of the collapse, the clean split, and the telltale chevron markings, investigators quickly identified brittle fracture, often a problem with weaker forms of steel dating from the 1940s and earlier, as the cause of the catastrophic failure in Floref. Brittle fracture has been known to plague a variety of older structures, even large ships. Tests revealed it was the main reason for the failure of this tank, which had been built in the early 1940s. And the weather compounded the problem. Sub-zero temperatures before and during the filling made the tank's old steel even more brittle. The exact location of the defect was also a factor. Welds are always weaker than the solid inner portions of a plate. When workers disassembled the tank in Cleveland, new cuts were made away from the original welds, since rewelding the same area can actually make it weaker. But when the tank was put back together in Pennsylvania, the defect happened to be in an especially dangerous spot.
The fracture occurred in this general location. This also is the location where a horizontal weld and a vertical weld come together. We call it a T-joint, and it's in this area that has particularly high stress concentrations.
Once a tank is built, welds, including T-joints, are inspected. To find defects that aren't visible on the surface, like the one in the Ashland tank, inspectors routinely use an X-ray system for metal, known as radiography.
The joints where the vertical seam and horizontal seam come together is a typical place where these radiographs are taken. That provided the opportunity to possibly identify this defect, but it was not identified.
Following the investigation of the spill, state and federal agencies put new procedures in place.
Pennsylvania implemented above-ground storage tank regulations so that tanks like this tank that failed are inspected routinely now, that they are tested routinely now in an attempt to avoid situations like this in the future. The federal government also changed its oil spill requirements in terms of equipment that needs to be available and precautions that need to be taken.
A federal grand jury indicted Ashland Oil for negligently discharging oil into the Monongahela River. The company eventually paid almost $7 million in state and federal fines.